All right, so we're on the home stretch for the course. Today is actually the last day in terms of new material that I'll be covering. Um, so we'll be completing hypothesis tests today, and then next Tuesday will be a review for our last test, test number 3, and also we'll have our last quiz, which will be on hypothesis test. It'll be a stat key hypothesis test quiz. And then a week from today is test number 3, which will cover confidence intervals and hypothesis tests. Also, the idea of those two are the basic concepts that we'll be covering in that test. And then the following Tuesday will be our final exam. Now, again, please notify me if there's any conflict, anything going on. You need to take, if there's some conflict, you need to take any of these things early, not late. My goal, after you take your final exam on Tuesday, which I believe is May the 4th, I believe, is to get all the grades completed that day. One of the reasons is because there is graduation that weekend. So if for any of you who are finishing up your course at Rowan University, then I want to make sure the grades are in. And also, my wife and I have some personal business that we have to take care of for a couple of weeks. We have put it off, but now we have to take care of it. So we're actually leaving the area on that Thursday. So there's a great incentive for me to get everything done on Thursday. So basically, everything else, the quizzes and the 3 tests, will all be finalized, and your grades will be all ready to go before the final exam. And then I just add the final exam part of it, and then it's done. Now, next Tuesday during the review for test number 3, I will also go over some points about the final exam also, all right, including how to do the written part of it on Canvas and how to use the functionality of Canvas to write your answers. Because there is a written part, because this course is a core course. And as a core course, that part of the final exam has to be written. So you're not actually going to write it on a piece of paper. You're going to type it into Canvas. And then I'm going to read it and grade it manually. And then the final exam also will have a multiple choice part of it too. And it is cumulative, the final exam. If there was any questions about that, it will be covered during the semester. All right, so people are still coming in. Let's get started. And what I'm going to do today is show you how to do the hypothesis test. There were 6 steps that I mentioned last time, and I'll show you the 6 steps again. And we'll do examples of how to do hypothesis tests in StatKey. Right? All right, so let's go to the PDF instructions. Share those. Okay. Why? Here we go. So let's go back to the introduction hypothesis test again, just once more to a quick review. Hypothesis tests are claims about populations, not about samples. We have a null hypothesis, which is the accepted state of affairs. And then we have an alternative hypothesis, which is a challenge to the null hypothesis. Some researchers challenging it. The null hypothesis is written in a similar way in this particular way here. So if it's there's only two types of parameters we're going to have a hypothesis about, and that's either a mean or a proportion. So this is an example here. You use H with a little 0 next to it, and believe it or not, you can type that in Canvas. There's a way of doing it. I'll show you next week. And then you put a colon next to it, and then Greek letter mu, and I believe you have access to symbols. So again, we'll go over how to enter a mu, this Greek letter mu. And then it says equal to 5. That's an example. Now, equal to is always in the null hypothesis, always. Here's another example of a null hypothesis using a proportion. P is equal to 0.35 is an example. The alternative hypothesis has one of 3 cases. If it's for a mean, we're either going to have greater than, less than, or not equal to. All right. And same thing for a proportion. Just one of these is going to be true based on the context of the problem. All right. You should be able to determine, looking at the problem, whether we have a greater than, less than, or not equal to case. In a hypothesis test, we assume initially that the null hypothesis is true, and we're looking for enough evidence, statistical evidence, using our sample to see if we can reject the null hypothesis, because it would be highly unlikely to get the sample data if the null hypothesis is true. It is highly unlikely to get the sample data. If the null hypothesis is true, then we reject the null hypothesis. That's what we mean by enough evidence. If there's not enough evidence to conclude that the null hypothesis is false, then our statement is that we do not reject the null hypothesis. That's the statement. We never ever say, this is what this last sentence means here, we never ever say we accept the null hypothesis when there's not enough evidence to reject it. We never say that. So if you write that down in the written portion of the final exam, or you choose that as a possible interpretation, it's false. You'll get that wrong. You won't get any points for that. And the reason for that is that because there's not enough evidence to reject the null hypothesis, it doesn't mean that the null hypothesis is true. It could still be false. And going back to that case where we have a criminal trial, if the prosecutor doesn't provide good enough evidence for you to find the person guilty of a crime, it doesn't mean the person didn't commit the crime. All right? I think that's pretty, that's common sense, right? Somebody could still have committed the crime. It's just there wasn't enough evidence to convict them. Same thing here. If the sample data doesn't provide enough evidence to reject the null hypothesis still can be false. That's why we have these errors here, these 2 types of errors, type 1 and type 2 error, which you are responsible for this test that's coming up. So what is a type 1 error? Well, our statistical test that we're going to be doing in StatKey indicates that we should reject the null hypothesis. When in actuality, the null hypothesis is true. Well, that's an error, right? If we reject it and yet it's true, we've committed what's called a type 1 error. On the other hand, if we do not have enough evidence to reject the null hypothesis, but the null hypothesis is false, that's also an error, and that's called a type 2 error. Now, the probability of a type 1 error is the one that we're going to be focusing on more when we do hypothesis tests. That's called alpha. And it's also another name for it, as you'll see down here, is level of significance. So we're going to talk about that today, level of significance. It's the probability of a type 1 error. Probability of type 2 error, we use the Greek letter beta. But that's all you need to know about beta, that it's the probability of type 2 error. We're not going to calculate it. Now, if I give it to you in a test and say, this is beta, and I say, what is the power of the test? Well, the power of the test is 1 minus beta. All right? Power of test is the probability that we reject the null hypothesis when it's actually false. That's the complement of beta. So if you know beta, 1 minus beta is going to be the power of the test. So you should write that down. And that's all you need to know about the power of the test. We want the power of the test to be as high as possible, because when we reject the null hypothesis, we do want the null hypothesis to be false. We want it to be a correct decision. All right, so the power of the test, we want that to be high. We want beta and alpha to be low. We want the error probabilities to be low. Now, again, alpha is the probability of a type 1 error. It's also called the level of significance. And this is something that is predetermined by a researcher, before they do any, they determine what level of significance they want for the research. In other words, what is the highest acceptable type 1 error that they're willing to live with. So many, in the social sciences like psychology and sociology, 5% seems to be a typical one, but you could use any percent, as long as it's low. Typically, we don't go above 10%, but it's possible that level of significance higher than 10%, but we want it low, all right? And so we're going to use alpha, the level of significance, as a way of determining whether we're going to reject the null hypothesis. I'll show you how that's done. All right. And again, there's 3 types of tests, hypothesis tests. There's a two-tail test. And how do we know two-tail test? Because when we create our 2 hypotheses, the null and alternative hypotheses, the alternative hypothesis has a not equal sign in it. It means that the researcher's saying that the 10, in this case here, is not true. They don't think it's true, but they're not sure whether the true value is, or mean is, less than or greater than 10. All right, they have no opinion on that. So they just say different than. All right, if you see the word different than 10, that's what the researcher's saying. It means not equal to. Again, common sense. All right, this is just common sense. And when we do a two-tail test, we have our alpha is going to be in the two tails. But we'll go over that in a little bit. All right, I'll show you how it works in a real situation. The left tail test means that the alternative hypothesis has a less than symbol in it. Notice that the null always has equal to. The alternative has one of 3 possibilities, in this case, less than. So we're going to do a left tail test. We're going to use the left tail. And then right tail test, the alternative hypothesis has greater than. I have this, hopefully this makes sense to you, right? Greater than, and notice the greater than symbol's pointing to the right, right? So we would use the right tail, and the less than symbol's pointing to the left tail, all right? So hopefully all of you have seen these symbols before when you took algebra in high school. All right, and then here's the steps of the hypothesis test that we're going to be doing, all right? Using what's called a randomization sampling distribution. This is something that you can, there's a video in StatKey, which I'll point out to you in a minute, which I would highly recommend that you listen to, even if it doesn't 100% make sense to you. At least some of it will make sense in terms of what we're trying to accomplish when we create this sampling distribution called a randomization sampling distribution. When we have the sampling distribution, well, first of all, the first step is to create our null and alternative hypotheses. And again, there's going to be 3 types, or 2 types, the mean or the proportion. Now, in this course, the math department has decided that in addition to the mean and proportion, you can also be tested on the difference in means and difference in proportions between 2 groups of people, 2 groups of things, all right? And I will show you examples of both of those. That was a decision somebody made. It wasn't my decision. So it is part of the curriculum, and it will be tested on in the final exam by the department, the core piece. So you do need to know all 4 types. That is the mean, one mean, or the difference in means between 2 groups, one proportion, or the difference in proportions. And I know it sounds kind of complicated, and again, nothing I can do about it. I have to cover the difference in means and difference in proportions. So I'll do the best that I can for you. Since the textbook that you have does not go over this at all. That's why I had to create these PDF documents. And also, obviously, we'll have the recordings of the video, which hopefully you'll go over again and watch exactly how I do these things, all right? So that's step 1, is we create our null and alternative hypothesis, and it's written like this. So simply, if you write it like this, it's great. Exactly as you see it, one of these 2, or the difference. I'll show you again the difference, how it's written out. All right. Please don't leave out the symbols. I've seen students do that. They don't know what symbol to put in there, so they just leave it blank. They'll say equal to the null hypothesis, equal to 100. Alternative hypothesis, less than 100. You get 0 points for that. You might as well not put anything down. So I'm telling you, write it, the whole thing down. All right. Just know a mean has to do with something we're measuring, and a proportion is something we're counting, right? We're counting the number of people in a survey who answer a question in a survey a certain way. And then the proportion is the number of people that we count divided by the total number of people we ask the questions. That's a proportion, right? So that is it. And you have to know the difference between a mean and a proportion. And I hope you all know that by now. Now, step 3, enter the original sample statistic as an endpoint in the distribution. That's something that will be given to you in the test or quiz whenever I show you a stack key display. You're not going to have to create a stack key display, fortunately, right? You don't have to do it, but you should know how to do it, because that way, when you see the result that I give you, you know exactly how it was done. So it can hurt, like I said before, to go into stack key. You know, after you listen to this video, after you listen to the stack key video on these types of hypothesis tests, it can't hurt to just go in and play a little bit. You can't hurt the program. It's impossible to hurt it. You're not going to damage anything. Just play around so you're familiar with it. So that's step 3. You enter the sample statistic, and then you determine what type of hypothesis test do we have. We have a left-tail test, right-tail test, or a two-tail test. So we'll do examples of all 3 of those. And then we're going to determine by looking at the stack key display what the p-value is. And then we're going to compare the p-value to this alpha, probability of a type 1 error, the level of significance. We're comparing it to it. And here's the decision rule. And it's simple as this. It's true for any case that we do. If the p-value that we determine is less than or equal to alpha, the level of significance, the decision is to reject the null hypothesis. If the p-value is greater than alpha, we do not reject the null hypothesis, and that's it. So you're going to be comparing 2 numbers. You're going to look at the 2 numbers. If the p-value number is less than or equal to the alpha number, we reject. If the p-value number is bigger than alpha number, we do not reject. You all know how to look at 2 numbers and determine whether one's bigger than the other. That's all there is to it. So it's arithmetic, right? It's not even algebra. It's arithmetic. You should all know this type of arithmetic, comparing 2 numbers and knowing which is bigger. And then there's the interpretation part, which I'll go over. All right. So let's stop sharing here. And one thing I did not do, I don't think, is open up stack key. So we'll go stack key. Give me a second. All right. So share my browser with you. So in the browser here, you type in stack key, hit enter. Enter. And again, with my browser, stack key pops up first. Remember, if any of you have not been into stack key, all right, on your own, do it. All right. If you've not, literally, if you've never been into stack key, even though we've been doing stack key for the last 2-3 weeks, you've never been in there, I highly recommend that you go in there and play with it and listen to those videos I mentioned to you. So I'm going to go over that again. If you don't do any of that, don't expect a good grade. I'm sorry, don't expect it. You're just not going to get a good grade, period. You can't just listen to the videos and not go into stack key and play with it yourself a little bit, because you really need to be familiar with what stack key is doing, at least to some degree. All right. Otherwise, it's not going to make any sense. The videos are not going to make any sense. I don't care what you look at. It's not going to make much sense to you. We're going to go in. Now, once again, if you want to watch the videos that StackKey offers, again, you click the this link here, Statistics Unlocking the Power of Data. That's the textbook, and that's, by the way, that's what I have. I have a copy of this. The department did not make this available to you, so again, I would have, but it does cost a little bit of money to get this get the ebook of this. Maybe that's why they didn't do it. I don't know. Anyway, if you click that, you have a list of different options along here. The videos are listed right there. And again, Introduction to StackKey gives you sort of a tour of StackKey in general, some of which we don't cover, by the way. So then much of that introductory video is just additional information about StackKey. The Bootstrap confidence interval one, that's the one for the confidence intervals. That's this one in the middle here. Again, highly recommend that you watch it. And then for the randomization test, this is the hypothesis test. That would be the first video here. Notice they're only 20 minutes each. So watch them when you get a chance. I would highly recommend that you watch these, all three of them, in that order. Watch the Introduction to StackKey, then watch the Bootstrap confidence interval one, and then randomization test one. And again, do that on your own, all right? And they're here. All right, and you should be able to pull these up on any, pretty much any browser, I would think. Don't do it on your phone. I don't know if they'll work on your phone, but certainly on a computer, they should work. All right, so let's go back to StackKey. Okay, so write down some examples here, which I will go over with you. Now, in this textbook, actually, let's go to the textbook. See if I have it available for you to see. Let's stop sharing this for a second. All right. Share this now. Again, you don't have access to the textbook, but I do have the. Let's see what's going on here. All right. So I need to go. Just give me a second here. Go to example 4.7. That's it right here. All right, we're here. So this particular data set is actually in StackKey. That's why I'm going to read it to you. It's described in this textbook. Just read through it, and then for number one, we'll see what type of hypothesis test this is. That'll be the first thing that we're going to do. And then we're going to state the null and alternative hypotheses, and then we'll actually go into StackKey and do the actual hypothesis test. All right, so let's read through it. It says arsenic-based additives. As you probably know, arsenic is a poison, right? Arsenic-based additives in chicken feed have been banned by the European Union, but are mixed in the diet of about 70% of the 9 billion broiler chickens produced annually in the US. That sounds scary. Many restaurant and supermarket chains are working to reduce the amount of arsenic in the chicken that they sell. To accomplish this, one chain plans to measure for each supplier the amount of arsenic in a random sample of chickens. So you understand that they get a whole bunch of chickens. A supermarket chain gets a whole bunch of chickens from a chicken supplier, and they're going to randomly select them through maybe simple random sampling or systematic sampling, randomly select a certain number of these chickens, and they'll measure the amount of arsenic in those chickens. Obviously, when they pull out these chickens to measure the arsenic, it's spoiled. Now the chickens have to be thrown away. All right, and that's the ones that are sampled. The chain will cancel its relationship with a supplier if the sample provides sufficient evidence that the average amount of arsenic in chicken provided by that supplier is greater than 80 parts per billion. All right, that's the measurement, 80 parts per billion. Notice they say greater than, all right? All right. Now, arsenic, is that when we measure arsenic, is it a measurement variable or is it a categorical variable? I'm asking you a question. Somebody yell out. Measurement?
Categorical?
What is it?
Is it a categorical?
Why is it categorical?
Because like arsenic is a type of poison.
Yeah, but we're giving numbers here. 80 parts per billion. They're measuring it. They're not just saying, does it have arsenic? Yes or no. That would be a categorical. If I said, does it have it? Yes. Does it not have it? No. But in this case, we're measuring it. So is this a categorical variable or measurement variable?
Measurement.
Yeah, we're measuring. We're whatever instrument or way that they measure arsenic, they're determining if it's greater than 80 parts per billion. That's the variable that's being measured. Would you agree with that? Everybody agree with that? Yeah. We're not counting the number of chickens that have arsenic. We're measuring for each of the chickens in the sample how much arsenic they have in it. That's measurement. We're measuring it. Now, how do they measure? I don't know. They don't describe the measuring process, but we assume it's legitimate and it's accurate and all of that. All right. Now, what is the if we're taking a sample and we're for each of the chickens in the sample, we're measuring the amount of arsenic. What are we going to summarize those arsenic numbers with? I mean, what is the summary statistic that we're going to use? Notice it says it right here, average amount. So what are we summarizing?
Mean.
The mean, yeah. Remember, there's two types, mean and proportion. Mean is for measurement variables, right? We're measuring something. And the other one, proportion, is going to be for categorical variables, right? We're counting the number, like in this case here, if we wanted to count the number of chickens that had arsenic, right, in them, that would be categorical, right? And we would use proportion, okay? But here we're measuring, so we're going to use a mean. So we're going to use that Greek letter mu. Now, we're not comparing different groups of chickens, right? Different groups of chickens, we're different. Actually, I guess we could have had two suppliers of chickens, right? Those could be the two groups. We're not comparing two suppliers. We're looking at just one supplier, all right? So this is a single mean hypothesis test that we're going to do. One mean. And can somebody tell me, now remember, mu is the Greek letter used for a mean. So use the word mu when you say something. What is the null hypothesis? It would be H naught colon, and then what are you going to put after that in this case? Somebody say the null hypothesis. Mu?
Equals 80 parts per billion.
Yeah, very good. Very good. And what would be the alternative hypothesis? I'll give you the hint in this last sentence here.
Mu is greater than 80 parts per billion.
Very good. There you go. All right, and then I'll just scroll down. You can see it right here. See it? So there is now the null hypothesis is always equal to. They're trying to make it simple for you. If you're going to be really precise about it, you would have probably said less than or equal to, right? Because that would be the complement of greater than. But because it's unnecessary to do that, they just put equal to for the null hypothesis. Always, you always put equal to. So this alternative hypothesis will determine what type of test we do. Remember, we have three types of tests. We have a two-tailed test, a left-tailed test, and a right-tailed test. Can somebody tell me which of those three tests we will do as a hypothesis test? Which one of the three do we do in this case? Do we do left tail, right tail, or two tail?
Left,
Okay, why left?
because the muse, we're testing to see if the muse greater than 80.
All right, well, think about that for a minute. When I say greater than, on the number line, which direction are you moving towards? To the left or to the right?
To the right, actually.
Yeah, yeah,
Yeah, you're right. Okay.
yeah. And notice, if you look at the greater than symbol, isn't it pointing to the right? You see it?
Yeah.
Pointing to the right? Yeah, that helps a little bit, right?
Okay.
So be careful with that. I've seen students do that, right? Where they say something like, if they say it's greater than, therefore I use a left tail test. Be careful. Greater than is pointing to the right. That's right tail test. Less than symbol points to the left. That's a left tail test. All right, good. I'm glad you said it that way because I want to make sure that you will always get that part right, right? You don't want to mess that part up. Okay, so we know it's going to be a right tail test. All right, so now that we know something about this problem, we're going to stop sharing this and go right into StatKey and do a hypothesis test for a single mean, because that's what this is. Now, on the right here, on the right, on this right column here, it says randomization hypothesis test. This is where we do our hypothesis test right here. And it's a test for single mean, so it's this first one here. We're going to choose that. Now, the people who created that textbook are the Locke family. I told you the 5 Locks, the mom, the dad, and the 3 kids. They're all statisticians. And so they created the StatKey also. So some of the data sets that are in StatKey are mentioned in the book, right? And this is one of them. So the button here, if you go into StatKey and want to play a little bit, this first button here is a list. If you hit the scroll down button here, there's a list of all the data sets that are in StatKey, and there is a way of entering your own data set in here. There's an upload file here that you can use, but we're not going to get into all that. I'm not going to make you do any of that. So, but there is the arsenic and chicken data set here. So they do have this one here. That's why I picked it. I'm going to click that one. All right, and the original sample, if you look at the original sample here, it only has 6 values in here. So we're going to have to make an assumption here that the 6 is adequate. All right, we're going to say that it's big enough to do a hypothesis test. It may, I don't know if it's true or not in this case, but we'll make that assumption. All right, so we'll say 6 is enough. Here are the 6 values, by the way. This is a dot plot here. You always see a dot plot in these boxes here. And here are the 6 values. And actually, if you went into StatKey and played around, you notice if you ran your cursor over these dots, it gives you the actual arsenic level for each one of these. So here's one that has 68 parts per billion arsenic. I think it's parts per billion, yeah. And this one has 75 parts per billion, and this one has 81 parts per billion. This one is 93 parts per billion, and the last one is 95 parts per billion. So if you average, if you added up these 6 values, all right, and they said there's 6 here, and divided by 6, you get an average of 91. You see where it's pointing here with 91 below? That's the mean. So that's the sample mean. That is X bar, X with the bar above it. That's the symbol for a sample mean. So for the sample that we have, that is the sample mean. All right, everybody clear on that? No questions about it. All right. Now, what we're going to do now, the technology behind creating what's called a randomization sample. These are samples that are created by the computer. Right? They're not real samples, but they're created by the computer using a certain type of technology, which we don't have to go into. The video goes into it a little bit if you're interested in that. But they create all these randomization samples, and then when we create enough of them, we have what's called a randomization sampling distribution. It's just a bunch of these samples. Now, each of the samples that are the fake samples are all going to have a sample size of 6. They're going to have the same number of points in them as the original sample. All right. So if I created one of them, for example, this one has also 6 of them, but notice that they're at different places along the number line. Here's one that's 64 parts per billion. Here's 2 of them that have 70 parts per billion, and here's 3 that have 123 parts per billion. That's a lot of arsenic there. You average these 6, you come up with 95.5, and that's the average for the randomization sample, not the original sample, the randomization sample. So we're going to create a whole bunch of these. I'm going to reset it actually. When you hit the reset button here, it just clears everything out except for the original sample. And in a problem, I won't tell you, but I'm going to create, in this case here, let me just look at this a minute. How many did I pick? I'm going to create 2,153 randomization samples. Why did I pick that? I just made it up. I just decided that's the number I want to pick. So I'm going to create not one of these randomization samples, I'm going to create 2,153 of them. And again, the computer does all the work. The only thing you have to do is hit these buttons up here so that they add up to 2,153. So it's 2,000. So I'm going to click this twice, 100, and then 53. Hit this 5 times. And this button, the 1 sample button, 3 times. You can see how I created 2,153 samples. Now you can just play around with this and again in Stackey and create any number of samples you want. That's your option. Okay. Now, in this particular problem, the null hypothesis, notice the null hypothesis is listed here as 80. Now, if you wanted to change this, you can go into here and put another number in here as the null hypothesis. Right? But in this particular problem, it's 80, and it actually is defaulted as 80 in here. But again, because it's a blue box here, you can click here and put another number in here. All right. So if I wanted to put 70 in here, I get 70 if I wanted to. Let's make it 80 because that's what the problem said. Now, there's nothing here written about the alternative hypothesis. How do I get the alternative hypothesis? Well, in Stackey, you check off one of these 3 boxes. If you check off the left tail box, remember left tail means less than. So if I click the left tail box, the alternative hypothesis will be mu is less than 80. If I click the 2 tail box, the alternative hypothesis would be mu is not equal to 80. If I click the right tail box, the alternative hypothesis is that mu is greater than 80. Is everybody clear on that? So it's basically which of these 3 boxes is being checked. That determines what the alternative hypothesis is. Now, in this case, the alternative hypothesis we know is mu is greater than 80. So we're going to click the right tail box here. In the end, I'm going to create, I have to do it again. I'm going to create 2,153. All right, I've created 2,153 randomization samples. This whole chart here, the whole thing that you're looking at here, is called a randomization sampling distribution. It is a distribution of 2,153 samples, fake samples. They're simulated samples, fake samples, of size 6. Now, how again is it created? Well, it's created in such a way that the mean in the middle here is very close to the null. Notice the null is listed here. So whatever the null hypothesis is up here, it's going to end up being in the middle here. All right. So whatever number is being put in here determines how these dots are created. All right. And again, that's all you need to know. Notice if I just run my cursor along here, notice that in the box on the right under randomization samples, notice it changes, right? Because whatever dot I have pointed to, that's the 6, that's the sample of 6 for that particular randomization sample. If I move it over here, I create different samples. You see how it's all changing? Notice that the mean, sample mean, is getting lower. If I go to the left, it's higher as I go to the right, like that. All right. Now, the way it looks right now is not the way you want it to look, all right? Because they have a bunch of red dots to the right here. The red dots are indications of the, how should I say it? They're indications of samples that are sufficiently far away from 80 that we may want to consider them to be unlikely. However, notice that the red dots are to the right of 98.75. Now, where did they come up with 98.75 from? It's sort of defaulted to that, all right? We don't have to worry about how the computer came up with that number. The question is, what do we need to put into this box down here so that we can actually do the hypothesis test? And here is the answer. You go back to the original sample. Notice the original sample has a mean of 91. That's the number we want to put into here. Now, let's go back to the instructions just for a second. And I'll show to you what I'm actually doing at this point here. All right. Let's go back to the steps. We've already created our null and alternative hypothesis. We've created our sampling distribution. We just did that. And we're at step number 3. Enter the original sample statistics as an endpoint in the distribution. So that's what we're doing. We're in step number 3 now. So the original sample statistic, let's go back to the stat key, is this 91. It's the mean of the original sample. Not the randomization samples, because there's a whole bunch of those. There's only one original sample has a mean of 91. So what we want to do, this is, now you're not going to do this unless you play around in StatK. Again, I would advise you to do that so it'll be easier to remember all this. But what I'm going to say is I'm going to put this 91 into the endpoint. So I'm entering it into the StatK graph right here. And I'm going to type in the sample mean, original sample mean of 91. All right. Now we're going to actually be able to do the hypothesis test. Because we have our distribution here, and we've put in our sample mean here, and this is a right tail test. What we're going to be looking at here is the probability, this is a probability, the probability of getting the sample mean of 91 or something more extreme than that, which in this case would be greater than that because it's a right tail test, if we assume that the null hypothesis is 80. Remember, the null hypothesis of 80 is assumed to be true at first. So we want to see how likely is it that if the true population mean of arsenic is 80, how likely is it that if we took a simple random sample of 6 chickens, how likely is it that we would get a mean of 91 or higher? And what is the answer? This number up here. This is the probability of that. It's called the p-value. The p-value. Let's go back to this right here. Back to the instructions. Right, p-value. All right. Now, the proportion to the right of the sample statistic for a right tail test is the p-value. Proportion of what? The proportion of dots. Of all the dots that are listed there, and how many dots are there? Let's go back. Go back to the graph. How many dots are there altogether? How many samples are there? Randomization samples, 2,153. That's the number up here. Okay. How many dots are there it's all these red dots. These are the red dots that are at 91 or higher for any randomization sample that has a sample mean of 91 or higher. That is all these red dots here. All right, that's that's these here. The number of red dots divided by 2153 is 0.11. Now you don't have to do the arithmetic here, do you? You don't need to count the number of red dots, which you could if you wanted to. Be kind of tedious doing that, but if you wanted to count the number of those and divide it by all the dots, number of red dots divided by all the dots, the 2153 dots, gives you 0.11. So 11% of all these samples have sample means at least 91. Okay? And this is called the p-value. So this is the proportion of all the samples in the sampling distribution that have a sample mean that is at least 91, at least the original sample mean, the size of the original sample mean. So it has at least 91. Now, this is the p-value. Now, what's the next step? So we know it's 0.11. Go back to the instructions. Here we go. Now, we didn't say what alpha is in this problem. But let's assume, now, by the way, it will always be given to you. Alpha will be always given to you in this problem, in these problems, always given to you. All right. So let's assume alpha is 10%. What is alpha again? The probability of a type 1 error. Remember, that's the maximum amount of type 1 error that we're going to find acceptable. What is the type 1 error again? Rejecting the null hypothesis when the null hypothesis is true. That's the type 1 error. So let's assume that as a researcher up front, you've decided 10%. If you reject the null hypothesis, you'll accept a 10% error. Now, anything bigger than 10% is unacceptable to you. Makes sense, right? If 10% is the maximum error that you want, then anything bigger than 10% is unacceptable. And that means we're not going to reject the null hypothesis, all right? We're going to say too much of an error here. Well, the p-value, which is sort of a measurement of the actual type 1 error, all right, is 11%. It's 0.11. So if the p-value is bigger than alpha, it's unacceptable. And if we're going to reject the null hypothesis, it's unacceptable. And therefore, we decide not to reject it. That's the whole idea here. So if the p-value is bigger than alpha, we're not going to reject because it's too much of a possible type 1 error. All right? It's too big. It's too big. Bigger than the alpha that we want. Now, if the p-value happened to be lower than alpha, that's within the acceptable range. All right? Because alpha is the maximum type 1 error. And if the p-value, which is the actual type 1 error, if that's less than that, we're okay with that. And we're okay with rejecting the null hypothesis because it's acceptable. So if the p-value is less than or equal to alpha, we reject. If it's greater than alpha, we do not reject. In this particular case, one we're looking at, p-value, which is always up here, is going to be 0.11. If we convert that to a percentage, that's 11%. That's bigger than a 10% significance level of significance. That's the alpha. And therefore, since this is bigger than alpha, we do not reject the null hypothesis. So let's think about the interpretation in this case here. That was our decision. We're not going to reject the null hypothesis. What's the interpretation? So we'll go back to the book, the actual textbook, in this case. Remember, they want to see if there's sufficient evidence that the average amount of arsenic chicken is greater than 80 parts per billion. If it is, then that supplier of chicken is going to be, they're not going to use the chain, right? The supermarket chain is going to say, forget it. We'll use another supplier. Too much arsenic. So in this case here, because for this particular supplier that we got the sample from, since the decision is to not reject the null hypothesis, our decision then would be, we would say something like, at the 10% significance level, now notice when we give our interpretation, we always state the level of significance first. That's the alpha. In this case, I leave it blank here. At the 10% significance level, if alpha is 10%, we would say there is not enough evidence. Not enough evidence to do what? Not enough evidence to not enough evidence to say that the supplier has too much arsenic. That's greater than 80 parts per billion. All right. Remember, we're only taking a sample of chickens from this supplier of chickens, only 6. And we're saying that there's not enough evidence to indicate that this supplier of chickens is providing an average of 80 parts per billion or more. No, you can't say that, right? We didn't reject the null hypothesis, which means we don't support the claim that of the alternative hypothesis that it's greater than 80 parts per billion. Since we can't say it's greater than 80 parts per billion, we're going to end up keeping that supplier. There's not enough evidence to show that the supplier is providing too much arsenic. Okay, so that would be sort of an interpretation here. Now, somebody else doing another sample of 6 chickens might come to a different conclusion. But for the sample that we're looking at, there's not enough evidence that the population of these chickens from this supplier has an average of greater than 80 parts per billion of arsenic, all right, per chicken. There's no evidence of it. There's not enough evidence of it. So we're not going to support the idea that the supplier is no good, and we'll keep the supplier. That's sort of what the interpretation means. All right, any questions about that? All right, so we're going to do another example now. And this one's on page 301 of the book. So let's go to the book here for a minute. All right, so we're going to go to page 301. We're going to look at an example of a single proportion question. Single proportion question. And let's see if this is the right one. All right. Let's look at this example here. Now, by the way, the examples I'll be giving you will not be as complicated as this one here. It'll be very straightforward one. But this example is just to illustrate how to do a hypothesis test with a single proportion. It says in a student survey, 250 students were asked to write down a 4-digit random number. It says here only 12 of the 250 numbers ended with a 0. All right, so 250 students just write down a 4-digit number, and out of the 250, only 12 of the students wrote a number that ended in 0. What would be a 4-digit number that ends in 0? It would be 2,530. All right, so the last digit 0. That's what they mean. So it seems unusual, right? Does this provide provide evidence that students don't like zeros in the last digit? All right, and they're not very good at making up random numbers. So for some reason, I don't like putting zeros for the last number for some reason. If the numbers were truly random, the last digit would have, now remember, a last digit of a 4-digit number, the last digit would have 10 possible numbers, right? 0 up to 9 through 9. So we would expect, if it was just random, that each of the digits that we could possibly put as the last digit in a 4-digit number would be a 10% possibility, right? If every digit in the last digit of a 4-digit number were random, we would expect a 10% chance of getting a number 0, number 1, all the way up to a number 9. Makes sense, right? 1 and 10. There's 10 numbers. So the question is 12 out of 250 significantly small enough so that we start thinking, wait, maybe this is not random. Maybe students actually don't like putting zeros in that last digit of a 4-digit number. All right. So again, a little complicated. Not the type of question I'll ask on a test. Now, the null hypothesis in this case is that the proportion is 10%. That is, it's random. All right. Basically, it doesn't, students just randomly pick 4-digit numbers. There's no reason that they will pick a 0 as opposed to a 1 for the last digit of the 4-digit number. So we expect that the proportion of these students that picked 0 for the last digit of the number would be 10%. That's a null hypothesis. That's random. It would be, if students don't like putting zeros there, we would expect far less than 10% of them would put a 0 in as the last digit. So our alternative hypothesis is p is less than 0.1. I'm showing to you because it's a little more difficult question. Now, we have our null and alternative hypothesis. Can somebody tell me, looking at this, if this is a left tail test, right tail test, or two tail test?
Left tail test?
Left tail, very good. Left tail. So we're going to have a left tail test. Notice that the numbers up here, that 12 out of the 250 numbers ended with a 0. All right, of the 250 students, each one wrote down a 4-digit number, and only 12 of them of the numbers had zeros at the end. So 12 divided by 250, if you do that, and that's we'll do it actually in StatKey now. We're going to go into StatKey. And we're going to go out. We'll go back to the original screen. You do that by hitting the StatKey button here. We're going to test for a single proportion. All right. And I'm going to edit the data up here and actually put in. Now, they do have examples here, different examples, but I'm going to create this one by myself. I know that we have 12 out of the 250, so the count is 12 out of the 250 that don't have zeros. And I'm going to put 12 out of 250, and notice the sample proportion is 0.048. Now remember, we would expect about 10% of the numbers to be have zeros in them, because if people were just randomly selecting numbers, they didn't care about zeros or not zeros as the last digit in a 4-digit number, we expect about around 10% of the numbers have zeros at the end. But in this case, we have 4.8%, so much smaller than 10%. The question is this so significantly smaller, so small that we can reject the null hypothesis? Now, the null hypothesis, notice up here, it defaults to 0.5 in proportion. So I'm going to actually change it to 0.1 because that's our null hypothesis. Okay, so I typed in 0.1. Now, remember, the alternative hypothesis was p is less than 0.1. So somebody yelled out left tail. I'm going to make this a left tail test. And I'm going to pick 1,610 samples. Again, I'm just doing that for the fun of it. 1,610. 1,610. There we go. Now, the sample proportion is 0.048. I'm going to I have to change that. This just defaults to this. These numbers mean nothing right now. So remember, down on the number line down here is where I'm going to put the original sample proportion of 0.048. So I'm going to click that, 0.048. And now this number up here is my p-value. This is the probability of getting a sample proportion of 0.048 or smaller, because we say or smaller because it's a left tail test, assuming that the null hypothesis is 0.1. And look at the probability. It's really, really small. 0.0031. It's so small that it doesn't even matter what we say alpha is, because alpha typically, people use alphas typically between 1% and 10%. This here, if we convert this p-value to a percentage, which means we multiply this number by 100, it's 0.31%. It's less than 1%. So even if I said alpha is 0.01 or 1%, this p-value is much, much smaller than alpha. So the decision is, what's the decision if the p-value is less than alpha? Anybody? Come on, you guys know this. It's in the sheet that I just showed you. The p-value is less than alpha. What is our decision? All right, you're worrying me. Come on. You must know this. It's p-value is less than alpha. We reject the null hypothesis. It says it where? Right in the handout. Let's look at the handout again. I believe I posted this already. Right here, step 5. Step 5, p-value is less than alpha, less than or equal to alpha, reject. This is clear rejection. The null hypothesis. We sort of suspected it because 0.048 is so much smaller than 0.10, but we had to confirm it by doing this comparison here. This is critical, folks. You have to know this part right here. You don't have to memorize it. You need to print this out and have it next to you when you take a quiz and a test. All right. I'm telling you, this sheet here is very important. Print out, have it next to you, so you can come up with the right answer. All right. So we're going to reject the null hypothesis because the p-value of 0.0031 is much smaller than if we said alpha is 0.01. We could have picked any alpha and it would have been reject the null hypothesis. And therefore, we would say, if let's say alpha is 0.01, we would say at the 1% significance level, there is enough evidence to conclude, there's enough evidence to support the claim that students don't like putting zeros at the end of numbers. They don't like doing it. There's enough evidence because we're rejecting the null. And we're saying it's much less than what we would expect, 10%. So it seems like students don't like putting zeros at the end of their 4-digit numbers or at the end of numbers in period. All right, so that's an example of a hypothesis test for proportions. We have 2 more hypothesis tests I want to cover over the next 7 minutes, but you get the idea here that when I give you these charts, you'll know exactly what you're looking at. Again, play with them so you become familiar with how these charts are created. If you don't do that, I'm repeating, you will not do well in this test because you're not gonna remember what you're looking at. You just won't. I don't care how many instructions I give you on a piece of paper. It doesn't matter. If you don't review this on your own and watch those videos, StatKey videos and all, and play around a little bit, if you do all that, you got a good chance to do well. But if you don't, it's going to be tough. I'm telling you, it's not going to be easy for you. So that's my recommendation. Now, let's see which one I'm going to do next here. Page 303. We're going to go to page 303 in the book. A couple pages later in the book. All right. Doesn't seem to cooperate here. There we go. Is this the problem here? Let me see if this is it. Yes. All right, here's the situation. Now we're going to look at the difference in proportions. So we're going to, typically there's 2 groups of people, and we're going to compare their proportions. for something. So let's read this study here. Now Pew Research, it says PEW Research. That's a very famous research group. Pew Research and the Pew family were a wealthy family. Anyway, Pew Research study conducted in July 2015 asked 2001 U.S. adults whether they play video games on a computer, TV, gaming console, or a portable device like a cell phone. So are they going to use a bigger device like a computer or a gaming console or TV, or are they going to use a small device? That's the two choices. Now there's two groups. There are 1,000 males and 1,001 females. And within each group, notice that 501 of the 1,000 males said yes, they played video games on the big device, I'm assuming. Yeah. And 477 of the 1,001 females said they played video games on a big device. All right. Well, I guess that's not what it's being said here. No, I'm sorry. They're just being asked whether they play video games, period. Right? The device doesn't matter. So out of the 1,000 males, 501 say they play video games. Out of the 1,001 females, 477 say they play video games. So what's the proportion? For males, it's 501 divided by 1,000. And for females, 477 divided by 1,001. Now, what are they asking here? Does this provide evidence of a difference in proportion playing video games between males and females? In other words, do males in general, does a larger proportion of males play video games than a proportion of females? That's really what they're asking here, all right? But they're not really asking that because they're saying, is there a difference in proportions? So the alternative hypothesis will be not equal to, because they're not making a distinction between whether males play more than females or females play more than males. They're just saying, is there a difference between the two groups? So if you see difference in proportions in the two groups, that's not equal to. That's the alternative hypothesis. Notice that the null hypothesis is always going to be that the two groups have equal, in this case, equal proportions. And the alternative is that they do not have equal proportions. All right, in this case, it's a two-tailed test. This is a two-tailed test. All right, so let's go to StatKey. And StatKey has a test for difference in proportions right here. We have two groups, difference in proportions. We're going to click that one. And by the way, this one is listed. This is video games by sex. Let's play video games by sex. It's right here. All right. Notice that the null hypothesis is already stated. Notice it's not within a box, so it's always going to be P1 equal to P2. All right. Now, how do we know which of these three cases that we use here? It's a not equal to. P1 is not equal to P2 is the alternative hypothesis. All right. So that would be a two-tailed test. We're going to click the one in the middle here. Here's the original sample data. Now, group one, by the way, you see the little 1 and the little 2 here. Group 1 is the males. Group 2 is the females. Okay. If we find the proportion of each group that watch video games and subtract the two, male minus female is 0.024. So for this sample, the difference in proportions between males and females watching video games is 0.024 or 2.4% difference. Now we're going to create, in this case here, I'm going to create 3,481 samples, 3,481. There we go. Now, here's our sampling distribution. Notice that red is on both sides now. Why? Because it's a two-tailed test. You're going to see red dots on the left, red dots on the right. Now, here's the deal. What's along the number axis down here is the difference between male and female proportions. The difference. Notice some of the differences are negative. The ones that are negative, the male minus female difference is negative, means females have a higher proportion for those negative numbers. And for the positive ones, male minus female means males have a higher proportion than females. Again, running your cursor along here changes the randomization sample. But remember, each of these dots represents a difference in proportions. All right. Now, another way of writing the null hypothesis would be P1 minus P2 is equal to 0. If you subtract the P2 from both sides, that would be another way of writing it. But in a test, if you write it P1 is equal to P2, it's the same thing. So P1 minus P2 is equal to 0 is the same saying P1 is equal to P2. In the same way, the alternative hypothesis is P1 minus P2 is not equal to 0. That would be the same thing as saying P1 is not equal to P2. All right. Now, the difference in the sample is positive 0.024. Notice that you have two numbers down here, one on the left and one on the right. One is negative, one is positive. I'm going to change the one on the right to the actual sample difference, 0.024. I'm going to change this down here because it's positive, 0.024. Now, what is the p-value? Well, I have two of these numbers. Now, the one in the middle, always ignore this number in the middle. It means nothing. Well, it does mean something, but it doesn't mean anything as far as you're concerned. All right. Now, by the way, I'm going to spend another 5 minutes on here. So for those of you who can stay, please stay. For those of you who have to leave, you can watch the video later. Here's the key with a two-tail test. The p-value is going to be the sum of these two numbers here, the 0.144 and the 0.144. Of course, you could just simply multiply 0.144 times 2, but it means the same thing. The p-value is going to be the sum of the two numbers on the left and right. They're the same number in most cases. So that's going to be 0.288 is going to be the p-value, not 0.144 with a two-tail test. You add these two up. Now, suppose alpha, in this case, the probability of a type 1 error is 0.10. Is 0.288 bigger than 0.10? Anybody?
Yeah.
Yeah. And what's the rule? If the p-value is bigger than alpha, what's our decision?
You accept the null hypothesis.
Oh, we never say that. Remember that.
Oh, wait. Hold on.
I'm glad you said that, but that's wrong. You can't say it that way. What's the other way of saying, the correct way of saying it?
Oh, it's like if one,
No, that's okay.
I know what it
we-
is. It's on the tip of my tongue.
Yeah, this is the way. We don't say accept the null hypothesis. We say we do not reject the null hypothesis.
We do. Okay.
There you go. But thank you for saying it that way, because that shows you the wrong way, right? We want to know the wrong way. We want to know the right way. The right way is do not reject the null hypothesis. Very good. And the interpretation would be here that there seems to be that the data doesn't indicate any difference between males and females in this case. All right. No difference between males and females in terms of what? Playing video games, right? No difference in proportions. There is a difference, but it's not significantly different. All right, so therefore, we would state there doesn't seem to be enough evidence to suggest that there's a difference between males and females in terms of playing video games. All right, so that's a nice example. I like that one. And the very last one we're going to do is a difference in means. So let's stop sharing here. And again, if you have to go, please go, but I do want to make sure that you see this last example also. All right. So let's share again the book. And this last one would be a difference in means. And this is going to be page 320. There we go. All right, so this one has to do was smiling. And here's the deal. If somebody was going to be punished for doing something wrong, and they were looking at a picture of that person, all right, let's say somebody was judging, a disciplinary panel was judging somebody. They're not seeing them in person, they're seeing a picture of them. Will they be more lenient if the person is smiling in the picture as opposed to not smiling? All right. So there's a thing called a leniency score, which determines whether they are being given preferential treatment because they happen to be smiling in the photo, regardless of what they did. All right. So it's an interesting little study that was done. All right. And so this is basically smiling versus not smiling. And we're going to look at the difference in the average leniency score between the smiling group and the non-smiling group to see if there's a significant difference in the means of these scores. All right, that's basically what it is. So now we're going to go to the StatKey, and StatKey does have this in their database. And we're going to go back again. This clicking the StatKey button takes us back to the main screen. We're going to go to difference in means. And leniency in smiles is the one that shows up here. Now notice that they have the two groups, the smile group. If you look at the original sample, they have two groups, smile versus neutral. So it's the smiling photo versus the neutral photo. Notice there's 34 people in each of the groups. N1 means the smiling group, by the way. N2 is the neutral group. Notice that each of these dots represents a leniency score, all right? So the higher the score, the more lenient they are, I'm assuming, all right? And that's true for the neutral group and this for the smiling group. Notice the average leniency score for the smiling group is higher. If you took these 34 values and averaged them, you get 4.912 for the smiling group, 4.118 for the neutral group. And if you subtracted those two numbers, you get 0.794. Now they say 0.79 up here, but it's actually 0.794 if you subtract those two numbers, if you want to be precise. Now, in this case, it's also, you want to see if there's a difference between the two groups. So the alternative hypothesis will be not equal to. So the null is that mu1, the two groups have the same leniency score, and the alternative is that they do not have the same leniency score. So it's a two-tailed test once again. Okay. Once again, you could say the null hypothesis, another way of saying the null hypothesis would be u1 minus u2 is not equal to zero, is equal to 0. And the alternative would be mu1 minus mu2 is not equal to 0. But again, either way is fine. And if you click the two-tail button in this case here, you'll know it's a two-tailed test. And in this case, I'm going to create how many? 2,153 samples. So this is the number of samples. And once again, the difference in the means between the two groups is 0.794. I'm going to be more exact. I'm going to subtract those two numbers, 0.794. It is a positive number. Remember, the null is always going to be 0 here. So if the difference in means is positive, you change this number down here. If it was negative, you change this number down here. I'm going to change this one to 0.794. All right. And now we have our p-values. Now, this number here is only 1/2 the p-value because it's a two-tailed test. The other one's down here. So make sure you add the two together. And then you add these two numbers together, you get 0.056. Now, if you don't add them together, you could end up with the wrong decision. Let's say the alpha, our probability of a type 1 error, our level of significance, is 5%. Now, if you add these two numbers together, you get 0.056, which is greater than 0.05, and therefore we would not reject the null hypothesis. However, if you forget to add these two up, which you have to do on a two-tailed test, not for the left tail or right tail test. There's only one of these boxes. If you forget to add them, and if you just compare 0.028 times 0.05, you're going to end up rejecting the null hypothesis. You'll come up with the wrong decision. So remember, two-tailed test, you just add these two numbers together, and you get the true p-value. You have to enter this number in first, like we did, and then you get the true p-value, and then you make your comparison between the p-value and alpha, and you come up with your conclusion. All right, so this was an example of a randomization test for difference in means. Now, in this case here, 0.056 is greater than 0.05, and our conclusion is at the 5% significance level, there is not enough evidence to conclude that there is a difference between the smiling group and the neutral group in terms of leniency. We would say there's not enough evidence to conclude that there's any difference between the two groups. Doesn't seem like pictures make a difference. All right, any questions about what I covered today? Because that's the four types of hypothesis tests: the single mean, single proportion, difference in means, and difference in proportions. All right, and I also gave you examples of left tail, right tail, and two tail also. All right, any questions? So once again, next Tuesday, we'll have a review. We'll review not only what we covered today, but also confidence intervals too. We'll refresh your memory about those. And also there will be a quiz on these randomization hypothesis tests. The same, it'll look very similar to what we did on the last quiz, except we're going to do them on hypothesis tests this time. All right, any questions? All right, so that's it. I'll stop the recording and I will see you. Go ahead.
Sorry, Professor. So you said Thursday. Today is our quiz, right?
Now, let me review the schedule again. Next Tuesday is our quiz and review for test number 3. Next Thursday is test number 3.
Okay.
The following Tuesday is the final exam. All right.
Okay.
We only have
All right.
three more meetings.
Yeah.
Remember, the final exam is 2 hours long. I'll go over that next time with you.
Okay.
8 to 10 p.m. 8 to 10 p.m. 8 to 10 a.m.
Okay.
All
All
right.
right, but all right.
All right.
Thanks.
Yeah, you're welcome. All right. Anybody else have any questions? Aaliyah, Tom? No? All right. See you guys next time.